Hello, welcome to Keeping It Classless Labs. My name is Matt Oswald, and today we're going to be talking about spanning tree, but more specifically, what I'm calling nerd knobs within spanning tree. And I call them that because I consider them to be very easy to configure, but not as easy to conceptualize. And we'll get to where that happens. But just keep in mind, this video is going to go through quite a few features. It's going to cover mostly, I would say, rehashing concepts that were first introduced at a CCNP level. So I would recommend that you be at that level before watching this video, else there's a few things that might not make a lot of sense. This is going to be a very focused, deep dive into these features. What it won't be, this video will not be focusing on any sort of fundamentals on spanning tree itself, such as what are BPDs, what is a root bridge, things like that. It's going to assume that you know all that, again, CCNP level at least, I would say, just to kind of get us up to that CCIE written exam level. So keep that in mind. A lot of these features are going to be talked about, are really only relevant in an 802.1d traditional spanning tree world. We're not really going to be talking too terribly much about rapid spanning tree or multiple spanning tree or per VLAN spanning tree or anything like that. This is going to be a pretty simple video, but it's just going to focus on some of these features that I think people struggle over in terms of conceptualizing on exams like the CCIE written exam. So let's get started. So the first half of this video is going to be spent talking about what I'm calling advanced features, or really, they all end in fast, incidentally, and a lot of these are familiar in terms of, yeah, I've heard that term before, I know port fast, but what does it really do, what is it not doing, things like that. Uplink Fast and BackboneFast are the other two that we'll explore. So that's going to be the first half of this video. Let's get into our topology. I'm going to keep it as simple as possible in terms of what we're going to be exploring. I have one topology that we can go over here, and this is really just going to keep everything simple. It's a largely theoretical environment. I have another topology that we'll actually use that corresponds to some physical equipment I have. Unfortunately, I only have 2 switches at the moment, which the timing is pretty bad, but I'm getting a few more for my own CCIE rack that I'm going to be using once I get to the portion of the CCIE where I need to lab things up. So we have switch 1, switch 2, switch 3. They're connected in a triangle, as you can see. What I would say in this topology, let's make switch 1 our root, and as a result, this link is going to get blocked. So port fast really doesn't have anything to do with this part of the topology. Let's just say this is going to be our distribution layer, right? Dist, and that's going to be this switch, and redundant distribution layer switch. So the idea here is that you have an access layer switch, and you have clients connected off of here. The topology northbound of switch 3 rather is where we're going to see our spanning tree topology. This is where our spanning tree topology really comes in handy because we have a loop, and it's very obvious that we have a physical loop. So that's bad. We don't want that. We need to be able to block one of these links, and spanning tree does a good job of doing it. However, when we're talking about client access, it's a little different beast because we don't have any switches down here, hopefully. And again, this is a very theoretical environment, so all of your users are good little users, and they don't ever want to cause you a headache. So they don't plug in any switches down here. Now keep in mind, we're going to get into the second half of this video and talk about instances where users do decide to plug in their own switches, and yes, I know that's a very common occurrence. So we'll get there. For now, let's just talk about port fast. Port fast is really just what makes our life simple in terms of allowing the users to get connectivity quickly. Jeremy Chara is a fantastic video trainer, and in his series, I believe it was CCNA, where he really talks about this. He mentioned that today's operating systems are booting in less than 30 seconds, and I would say, yeah, very, very much so. In fact, many endpoints now, especially with the presence of VDI, are booting their little thin clients in a couple seconds because it's all flash based. So yeah, the need to get instant connectivity is very, very much is very important in like an office environment, or really anytime you have clients connecting into a switch like this. So port fast really is not too complicated in this respect. When we enable port fast, and it's on a per port basis, what we're saying is instead of waiting the 15 seconds in listening and 15 seconds again in learning, a total of 30 seconds at the very least without any other delays, 30 seconds at least of just simply waiting for the port to come up where the switch is saying, hey, do I have any BPDUs on this link? Let me just sit here and wait for any BPDUs. It obviously won't hear any because this is a simple client, and we're just going to be sitting here idle until that link comes up. So PortFast basically disables all of that. PortFast says, nope, you know what? I can guarantee, as the administrator, I can guarantee that I'm only going to be able to see a PC on this and not another switch. So I can guarantee a loop-free topology just because I say so. So by enabling PortFast on a port, and it is on a port-by-port basis, we're saying let's just not go through those 15 seconds states. And as soon as you get a link light, go ahead and go to the forwarding state for spanning tree. Now, obviously, you wouldn't want to configure that on these ports. That would be counterintuitive, or counterproductive rather, because then you certainly would not have the automatic blocking here, and you would basically intentionally create a looped topology. So obviously, that's bad. I would never recommend configuring PortFast on a topology like this. But PortFast on an access layer switch facing southbound to something that you know never will produce loops, it's actually not too bad. Now again, we're going to get to a point in this video where we talk about features that help prevent nefarious users, or even just users that weren't aware that they were causing a problem. But we'll get to that later. So that's PortFast. PortFast, in a nutshell, it's not inaccurate to say PortFast simply disables spanning tree on a port. That doesn't mean the port is no longer part of the spanning tree topology. It just means that those listening and learning states are no longer going to happen on that port. It's just going to go straight to forwarding. Okay, so the next feature we're going to talk about is called Uplink Fast. Now, Uplink Fast I've found to be, at the front end, a little confusing as to the function of it, especially if you're talking about a CCNP level or CCIE Written level knowledge of spanning tree. Because, as I mentioned, there are some features that are actually integrated into future iterations of spanning tree, like rapid spanning tree. And Uplink Fast is one of them, or at least some of the ways that Uplink Fast works is integrated into rapid spanning tree. And we'll get there when we have I'm actually working on a post now about specifically rapid spanning tree and how Uplink Fast plays a role there. So keep that in mind. Uplink Fast is sort of the predecessor in terms of just a feature to rapid spanning tree, which is the standardized format of really fast convergence of spanning tree. So Uplink Fast, in a nutshell, is aimed at converging from a failed spanning tree, a spanning tree environment that has failed in some way, a link's gone down, something like that, reconverging onto another link to work around the problem and get back to a stable spanning tree state quickly. With, again, traditional 802.1d spanning tree, not rapid spanning tree. So Uplink Fast does this in an interesting way. Let's bring up our topology here that we looked at for PortFast. Let's again elect a root bridge, and switch 1 has been a good root bridge, so let's do that. Switch 1 is our root bridge. Again, the link that's going to get blocked, and I forgot to mention this in the previous feature, PortFast. I said that this link is blocked just simply because in a topology like this, you have equal cost ports, things like that. This link is going to get blocked because the cost for these two links is equivalent, and both switch 3 and switch 2 is going to see the link across here as a less desirable link to get to the root bridge. So that's the link that's going to get blocked. Just wanted to mention that. I'm making an assumption. This is a very theoretical environment, so I'm just saying all costs being equal, that link's going to get blocked, assuming switch 1 is the root bridge. So anyway, Uplink Fast is going to enable us to do some rapid reconvergence in the event of a failure. So switch 3 is really our perspective here. We're sitting down on switch 3 and we're an access layer switch. This is where access layer switches aren't the only place where this can be used, but it certainly comes in handy at that layer. And the reason for that is because we have dual connectivity up to, let's say, our distribution layer up here. And our root bridge is switch 1, and let's say somebody trips over a cable and cuts this guy out completely. So that link is dead. Switch 3 sees this, and in a normal non-Uplink Fast scenario, again, has to wait the at least 30 seconds of listening and learning to even bring this link up online. And this switch could have many clients on it, so you're talking about some serious downtime. So Uplink Fast aims at getting around all of that. Now, as I mentioned in the last video, you could certainly enable PortFast on all your ports, but then again, that would cause a loop, so you don't want to do that either. You would like spanning tree to block the link, but you don't want it to stay blocked for a long time after a failure has happened. You want it to very quickly come up in a safe way. So UplinkFast does this in a multi-step process. The first thing, and this is configured, UplinkFast is configured globally on your switch. So we flip a bit and we say, you know what, I want UplinkFast to be configured here. And what UplinkFast does first is it sets the root priority to 49,152. Which is very undesirable as far as priorities go. That's the default priority. Even the default priority for a switch is 32,768. So this is very undesirable as priorities go. The other thing it does is it's going to set all port costs to 3,000, which is just as bad. 3,000 is abhorrent as far as port priorities go. In fact, a 100 megabit link is going to be a cost of 19. And in today's networks, even a 100 megabit link is pretty small. So 3,000 is abhorrent, and you might be asking yourself, well, why would it want to do that? The reason for that is, again, you're configuring this globally on a switch that you'd never want to be the root. An access layer switch should never be the root bridge of really any network, unless that's all there is to it. If there's any sort of hierarchy in a network, you would never want the lowest level to be the root bridge, because typically that's where your smaller devices are, where all of your users plug in, and it's really just a matter of getting the users to be on the network in the first place. In terms of handling the backplane and the throughput and all of that, the root bridges should typically be some beefier switches. Now we're talking really anything it could be anything depending on the environment. Let's say the Catalyst 4500 series or the 6500 series, something that can handle the load. Those are great root bridges because they're built for that kind of stuff. So UplinkFast says, you know what, I'm an access layer switch or something that should never be the root. So I'm going to set my priority and my port priority really, really, really high so that would never happen. The other thing that would happen is, and again, this is before our failure. So let's take this poor failed link back online. Oops, I'm undoing the wrong thing. Let's just say this guy is still living for the time being, because we're configuring this before our failure, and we've set our as part of the configuration, the priority has been set to 49,152, and the port priority for all spanning tree ports is now 3,000. So in addition to that, UplinkFast is going to say, well, you know what, I've blocked this link. And obviously, this side of the link is going to be what's going to be blocked because its priority is really, really, really high. So switch 2 is actually going to be the designated port over here, port 2, and then this is just going to get blocked. If I can write today. So switch 3 sort of controls this topology and says, you know what, I've blocked this port, but I know that it's an alternate path to the root because that's why I blocked it in the first place. I heard superior BPDUs received on this path. They just had a cost that was higher than what I wanted. 19 plus 19 versus just 19. So that's okay. It's going to get me to the root bridge. It's just going to do it over a higher cost path. So I'm going to block you for now, but I'm going to keep track of you in case this link were to fail. So that's really what UplinkFast does, and what makes it fly. So let's say that failure does occur, and this link gets broken. So now we have a backup path. We now have an alternate port that we can now use. Within seconds, really, this port says, okay, well, you're my alternate port, and I've stopped receiving BPDUs from my root. So now I'm going to light you up and say, yep, you're good to go. So that's really what UplinkFast is designed to do. It's designed to reconverge the network very quickly, and it's designed to allow you to keep track of alternate paths to the root where normally a spanning tree bridge would just simply not care. It would need to essentially recalculate every time. One thing I want to mention also, UplinkFast is going to flood a multicast frame for every MAC address in its CAM table. So it goes through and it says, okay, I'm looking at MAC address 1, 2, 3, 4, 5, blah, 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 blah. And for every CAM table entry that it sees, it's going to flood a multicast frame. And in each frame, it's going to have that MAC address as the source address. Now, the point of all of that, once this backup link comes up, is switch 2 is going to hear all of those frames and it's going to relearn all of those MAC addresses now on port 2, where before it learned them on port 1 because that was the way to get to switch 3. Again, this link was blocked before. So that's a really cool way of instructing switch 2, hey, by the way, those MAC addresses have moved. You don't need to wait to age them out or anything like that. They've moved. Just start to communicate with them on this new link right away. Again, the goal is to reconverge quickly, not just in spanning tree concept, but in just traditional switching concepts. So I wanted to take a quick detour after we've explained the concept of UplinkFast and look at some real switches. Again, my ability to lab some of this stuff up for you is going to be limited. I have a few additional switches coming in, but the topology here is actually much simpler. I only have 2 switches right now. One's a Catalyst 3560, the other one's a Catalyst 3550. And it's switch 1 and switch 2 respectively. So the one on the right, switch 2, is the 3550. And really the only thing I wanted to show you was just that when you do configure UplinkFast, it's very simple. Again, most of these concepts are one-liners, if that. So you really don't have anything to worry about in terms of configuration. It's just conceptualizing all of these things. So we go into global config mode, and really, well, let's first see where we are. We're running IEEE spanning tree, so just traditional 802.1d, nothing special, and we don't even have any priority set. 32.768 plus the VLAN 80 of 1 results in a priority of 32.769. So the one thing I want to do just is configure UplinkFast, and it's very simple. Spanning tree, UplinkFast. And I don't even think there's an option after that, a max update rate. That actually warrants a little explanation. Max update rate is pretty simple. That refers to that last point that I made on the MAC address table. Flooding essentially is going through all the MAC address tables and the MAC address table entries and broadcasting them, or rather more accurately multicasting them to all connected switches to make sure that those MAC address tables in the other switches are updated correctly and quickly. And really, the max update rate just says, you know what, let's tone that down. If we don't want to just spew all of the MAC addresses. If there are a large number of them, let's throttle that down so that we don't overload the switch and kind of defeat the purpose of reconverging quickly. So that's what that's for. But really, that's the only option after this. You can certainly hit enter, as we can see, and we'll do that now. And if we do another show spanning tree, we can now see that our own priority has been set to 49,153. So essentially, we've in fact, if I recall, okay, no, we weren't the root. I thought that we were the root originally, but certainly we're no longer the root because of our huge priority. And also, as you can see, we now have a port cost of 3,000 plus the actual cost of the link, so it increments it by 3,000 and then adds the port cost on top of it because this is a fast Ethernet link. And as we can see, also UplinkFast is enabled. So those are the 2 methods that spanning tree UplinkFast uses to ensure that the switch that you're configuring on would hopefully never ever be configured or be elected rather as the root bridge. Okay, so the third feature that we're going to talk about in this section is called BackboneFast. Now, BackboneFast is actually pretty simple as well, but it's aimed at doing something a little differently. BackboneFast is all about indirect failures. As we could see in the previous topology when we were talking about UplinkFast, we didn't have to wait for any sort of max age timer to expire, so that when you stop receiving BPDUs, then the reconvergence kicks off, or more accurately, we didn't receive any BPDUs with the TCN bit set. None of that happened because when we experienced that failure in the previous topology, we experienced a direct failure. Whenever a switch sees a link down that's part of an active spanning tree topology, it immediately knows that a reconvergence is necessary. Especially if that port was a root port, UplinkFast says, well, I've lost my root port, so now I need to go to my backup route, basically, the one that I was previously blocking. I'm going to now forward that. But what happens if there's a failure further up the line and for whatever reason a TCN BPDU has not been sent? Let's say it's our access layer switch again. So let's bring up the topology that I'm talking about, and it'll make it a little more clear. I've added a switch to the mix because I want to be able to show you the indirect failure that's going to happen. So let's keep things as consistent as possible. We still have switch 1 as our root bridge. And we're really going to go through here and talk about links that we're going to block. So we've got our topology set up here, and switch 1 again is our root bridge. And I've added a switch 4 here because the point of this this exercise is to show the impact of an indirect failure. So let's say we've got plenty of opportunities for loops here. Let's get one out of the way here and block the link that we've been blocking previously. We still have a loop on the outside, so spanning tree is going to say the lower bridge ID wins in this case. So the link between switch 4 and switch 2 will stay up, which means that switch 4 will have to block this link, the higher switch ID. I'm just going off the host name, by the way. But this host name is equivalent to the last character in the bridge ID, therefore it's higher. So that's my logic. I'm sticking to it. So switch 4 has blocked that link, and now we have a loop-free topology. So let's say switch 2 experiences a direct link failure. Let's say somebody trips over this bad boy and says, you are down. So switch 2 actually has no communication with the root whatsoever now because this link is blocked and its root port just got kicked out. So it has no way to send a topology change notification to the root. Again, TCN BPDUs are not broadcast. They're sent to the root, and if the root receives it, then it filters it down. But if the TCN BPDU doesn't get to the root, then it has to, all the other switches have to rely on their max age timers to expire, and once that happens, then they can reconverge. But you're looking at least 20 minutes, or I'm sorry, not 20 minutes, 20 seconds by default. The max age timer, 20 seconds. So that's a little longer than we'd like. What we need is a way for switch 4 to ask switch 2, hey, I've stopped receiving BPDUs from you, which really are from the root, but you've been my method of getting them. What's going on? Have you experienced a failure of some kind? That kind of thing. So, because again, the TCN BPDUs aren't being sent to the root because that link is down. It's not possible now. Switch 4, if you've configured BackboneFast on switch 4, if it misses one expected BPDU, so exactly one hello timer, which is 2 seconds by default, if it misses one hello BPDU, at that moment it will send something called an RLQ, or a root link query, to switch 4. And an RLQ is designed to really just do one thing, saying, hey, are you okay? It's sort of just a question of, I've missed a BPDU from you. Have you experienced a direct link failure of yourself? And now switch 2 can respond directly and say, well, yes, I have, and it actually responds with another RLQ packet, frame rather, sorry. And then switch 4 immediately is notified of that failure and is now able to reconverge without having to wait for its own max age timer to expire. So it can do stuff like bring up this link and get to the root that way. Not an ideal path, because the ideal path is through the lower bridge ID, but at the very least we now have access to the root. And in this specific topology, all links are equal cost anyway, so switch 4 doesn't really care which path it goes up, because the bandwidth is the same, the cost is the same. So keep that in mind. BackboneFast is really all just about indirect link failures. So now we're going to talk about the second half of this video, which is really all about protecting the spanning tree topology and making sure that events that are not really events that we can't control, things like people tripping over cables, or the more malicious users plugging in switches into their switch ports and their walls, things like that. Events like that won't have a significant impact on our spanning tree, doing our best to protect the topology from things like that. So the first thing is BPDU guard, and BPDU guard is actually pretty cool. So I mentioned before, when we're talking about client access, clients are going to be connecting to this switch down here, switch 3. And I don't have the right tool out. Silly me. Clients are connecting to switch 3. And I mentioned before, in a perfect world, users don't plug in switches, but the reality is they do. So what we want to do is put ourselves into a position where we can look at switch 3 as an access device that has port fast configured on all the ports that it needs to. BPD guard is something that we can configure on top of a port fast enabled port, or maybe just a regular port, whatever. But it is most widely used in this implementation because we want to provide users with that quick uptime, something that says when the link is up, spanning tree is forwarding. We want that feature, but we also don't want them to be able to plug in something like a switch where they get the ability to increase our spanning tree diameter for one, and two, potentially induce loops. In fact, as I don't know if anybody else has run into this, but I have. I was surprised when I heard it for the first time. I was like, no way, no users would ever do that. But I've heard of users plugging in a small switch in one port and then taking another port on that switch and plugging it into the wall jack next to it. And the logic there, I don't know why, but the logic there was, well, it'll increase my bandwidth because I've got 2 ports plugged in. It's what they're doing these days. Don't ask me why. I'm not in that mindset. It's just the way that it's happening. So keep that in mind. These things actually do happen, and probably more often than you care care to have to deal with. So BPD guard is actually quite friendly for the network administrator. BPD guard really does nothing more than listen for BPDUs on a port. And if it hears them, it places it into an error-disabled state, which is essentially the same as bringing the link down, saying, you've plugged in a switch, you're trying to multiplex one port into many ports, doing whatever you need to do. I'm just going to nip that in the bud right away and bring down this port. So you can do this in 2 ways. You can enable BPU guard and call it a day, and whenever that port goes down, what you'll actually have to do is go in and shut and then no-shut the port to get it to come back up. Some users, or rather some administrators, like to do this because that forces the user that plugged in the switch to go to the IT department of his or her company and ask for that port to be brought up. Well, user, why do you need the port to be brought up? Did you plug something in you shouldn't? That kind of thing. There's also another feature for those that aren't like that. They don't want to have the conversation. They also have a feature on Cisco devices, at least, that allow you to bring the ports up after a certain amount of time. And the cool thing about that feature is it allows you to bring them up per reason. There's actually quite a few ways that you can place a port into an error-disabled state beyond just BPU guard, and that feature can be configured on a per reason basis. And it's all based off of number of seconds. You can spend, let's say, 5 minutes, 300 seconds in an error-disabled state, and then you can bring you can bring yourself back online if you wish. Next in the list is BPD Filter. I'm not really going to talk about this a lot, and I'm really not even going to change my topology at all because BPD guard and BPD Filter are actually quite similar. BPD Filter, for the data center guys out there, as I am one of them, and I'm always interested in anytime a non-networking company rolls out networking features, I'm always interested. I was at VMworld 2013, or I'm sorry, 2012. 2013 hasn't happened yet. 2012, and that was when they announced vSphere 5.1, and that's when they talked about BPU filter as an option included in the new vSphere distributed switch. And I argued that they should have implemented BPU guard, but that's a discussion for another day. BPD filter is actually pretty similar to BPD guard, with the exception that BPD filter does not place a port into an error-disabled state. BPD filter simply drops all BPDUs that are received on the port, and that's basically it. Every time you receive a BPDU, you get dropped, you get placed in the bit bucket. So next on the list is root guard, and root guard's pretty cool because root guard allows us to protect ourselves against users plugging in devices, and if you have BPU guard configured, that weeds out the majority of the unintentional problems. But let's go a little deeper. Let's say there's a nefarious user in the network, and him or her are bringing in some sort of a device that sends out well-crafted BPDUs to try to get their device elected as the root, which, let's say, at best, they're trying a man-in-the-middle attack, and at worst, they're simply bringing down your network just because. Root guard's interesting because it allows us to specify ports that should never become root ports. So let's go back to our trusty topology over here, and let's say that our desire is to keep switch 1 as the root, as it has been in this entire video. And let's say a user gets, or a hacker, let's call him a hacker, smile, sad face, gets into this switch and says, you know what, I'm going to change this switch's root priority so that I become the root. Or let's just say something a little more practical. Let's say they're plugged in as a PC, and that PC is spoofing BPDUs into the switch. However we want to do it, there's some rogue BPDUs making itself into the topology, and one way or another, there's another device vying for that root bridge position. So on switch 1 and switch 2, and that's really where you would want to configure this, you can say, look, I know for sure that this port is never going to be a root port. And switch 2 says the same thing on its second port here. I know for a fact that this will never be a root port. So when you're talking about a topology like this, and you know those ports would never be a root port because, again, this switch 3 would never, you would never want switch 3 or any device on this layer to be a root bridge, you can enable root guard on these ports so that if switch 1 and switch 2 receives a BPDU, or more accurately, we'll call it a superior BPDU, a BPDU that if this feature wasn't enabled, then it would place that port into a root port state. Essentially, what it does is it ignores any received superior BPDUs to prevent that switch port from becoming root. Upon receipt of those superior BPDUs, when it receives those BPDUs, it actually places that port into a state called root consistent, or rather root inconsistent, which means that it's essentially blocking. It's essentially the same as spanning tree blocking. So consider this to be sort of BPDU guard for the distribution layer. We know that we never want to receive BPDUs that are being listed as superior to either of these switches because we know that we've built the network in such a fashion. So root guard is a pretty interesting way of doing that. So finally, the last thing I want to talk about is unidirectional link detection, or UDLD. And the concept of preventing unidirectional links isn't really anything new. However, UDLD as a protocol is a Cisco proprietary feature. Other vendors have very similar features that do functionally the same thing. And that is obviously to prevent unidirectional links. But before we get into how that works, I want to talk a little bit about why we don't want unidirectional links, why unidirectional links in general are a bad thing with respect to spanning tree. So we have our trusted topology up here, and as usual, we have switch 1 as our root bridge. And in this topology, we've seen this link get blocked traditionally because of the cost of all the links being equal, and this being the least optimal path from switch 3 to switch 2, or to the root from either of those. And the problem with this topology in, let's say, so you've got, let's just make this really, really practical. You've got a campus network that's shaped like this, right? Again, our access layer switch is down here, and then this is our distribution. Typically, this is going to be something like fiber because these switches could be anywhere in a campus. And generally speaking, those switches are far enough away that it warrants a fiber run. It could be some closet somewhere. Copper is usually not very convenient. So fiber it is. And fiber is really what I'm talking about when I'm talking about unidirectional links. Copper cabling, Cat5, Cat6, it can happen, but it's extremely rare because of just the fact that there's more pairs essentially in the cable, and there's more protection involved. The medium is bendable, whereas fiber optic is definitely not bendable, seeing as it's glass. So this whole idea of a unidirectional link is much more common with fiber optic because usually it's attributed to some sort of cable failure. So what does unidirectional links have to do with spanning tree, and really why is it so bad? Because if we have a unidirectional link, for sure, we're able to transmit but not receive. Obviously that's bad because we can't transmit data, but what impact does that have on our spanning tree topology? Well, unidirectional links can be very bad with respect to spanning tree because this topology on these links, whatever side of this link is blocking the port, is relying on a constant transmission of BPDUs from the root to keep that link down, essentially. So let's say, I think it was the last thing we saw, switch 3 was blocking this port because it sees BPDUs being received from the root or being received from switch 3 that are being transmitted by the root in this direction and in this direction. Now let's just say these are all fast Ethernet ports, so this is going to be 19, this is going to be 19, this is going to be 19. Obviously the path that is a total aggregate cost of 19 is going to be better than the one that is a total aggregate cost of 38, which is this entire route. So that's why switch 3 says, you know what, this is not for me, I'm going to use this as my root port instead. So switch 3 blocks this link, but that doesn't stop the BPDUs from being received, because switch 1 is going to keep sending them out all of its designated ports. And switch 2 is going to say, well, I have a designated port here. This side's not being blocked, so I'm going to forward these BPDUs on down. That's why switch 3 keeps this port in a blocking state, because it constantly receives these BPDUs that are less preferable to this path. So a unidirectional link, and let me clear out some of this crap just so that you get the idea of really the impact of a unidirectional link on this topology. So again, we're blocking on this port, and we're relying on the constant transmission of BPDUs, but let's say this is a fiber link and it gets cut in one direction. One of the strands gets stepped on, yanked out of the port, I don't really care, just some way the strand gets cut. And because of that, the strand that's cut is what's the data that's being carried is the transmit side from switch 2's perspective. So all of those BPDUs that are being sent from switch 2, or rather forwarded from switch 2, are no longer getting to switch 3. However, switch 3 has a forwarding path, at least, from switch 3 to switch 2, because this side is working. So this side is the side that's not working. So we do have communication in this direction, but we just don't have communication in this direction. And that breakage has stopped the BPDUs from getting to switch 3 successfully. So switch 3 sees this as a potential topology change. Since it's not receiving these BPDUs anymore, it starts to see this as a viable link. So as soon as the max age timer for the BPDUs that were being received ages out, it's going to place this link in listening state, and then learning, and then eventually forwarding. The problem with that is that we still have an active path to be forwarded out here, so broadcasts and any other flooded traffic is going to still loop around the network because of this link being brought online. So it's going to loop this way and continually loop around and cause a broadcast storm, essentially, or more accurately, a bridging loop. So the problem with unidirectional links is really all about what their impact on the BPUs and what switches are going to be receiving them, or more importantly, not receiving them. And when you bring up links that should be blocked because of this, then you encounter problems. So the problem statement is, we need a way to detect unidirectional links. So I broke down a very simple topology here for you. It's just a single link. So imagine this link is what we were just looking at in the larger spanning tree topology. And I've broken it out into two pairs, the receive pair and the transmit pair from switch 1's perspective, and then the reverse is the case on switch 2. So we have a fiber optic link, and somebody comes in, and I continually forget to get my tool brush out. So somebody steps on this link and says, well, we are going to step on this because we are clumsy. And as a result, switch 1 is no longer receiving BPDUs from switch 2, because the receive pin, or sorry, this is fiber, the receive strand on switch 1 is no longer working, but the transmit is. So the link is up, but we just aren't receiving BPDUs anymore. So this is what's going to cause our bridging loop, as we saw before. Now, UDLD is an interesting concept. It is a Cisco proprietary feature, but there are similar features on other platforms, and it works on messaging basis. So you establish essentially a neighbor relationship with the other switch using the UDLD protocol, and you enable UDLD on a port, and you enable it on the other side as well. And essentially, UDLD works in a couple different ways, but we'll start simple. The most basic way that UDLD works is that every 15 seconds, which is the default timer, UDLD will send out a message saying, hey, switch 2, are you there? Switch 2 responds, why yes, yes I am. And that essentially happens every 15 seconds by default, and then life goes on. At some point in this unidirectional link occurrence, when this strand does get cut, that message isn't going to make it to switch 2, so of course switch 2 is not going to respond with a yes I'm here. It's just switch 1's going to hear nothing. And in the normal UDLD mode, really nothing happens. It says this port has basically an undetermined state, and it will also generate a syslog message. Now, the important thing to note is that UDLD also has a second mode, which is aggressive. And typically, if you are going out of your way to implement UDLD, you choose this because essentially the goal of this, again, remember, we are implementing this on links that we want to stay blocked. So if our spanning tree timers 15 seconds for a forward delay, which means that we have a total of 30 seconds between the time that the link started to become unblocked and the time that it's fully forwarding, to figure out this whole UDLD mess. And we don't want UDLD to take longer than 30 seconds because then it would defeat the purpose and we'd have a forwarding loop before UDLD even does anything. So we don't want UDLD to take very long to detect a unidirectional link. So since the hellos that are sent between the two switches are happening every 15 seconds, that's the most that it will take to detect that state. Now, UDLD aggressive mode, as I mentioned, is what usually network engineers that are implementing this, they'll usually use aggressive mode because the goal is not to simply notify the administrator that it's taken place. We want to automatically and actively take that potential spanning tree bridging problem, or rather the bridging loop problem, out of the mix before it happens. And aggressive mode is what does that. See, aggressive mode, when you miss one of these handshakes, it immediately sends another message, essentially, one every second in rapid succession. Man, I cannot talk today. I actually need some water. So a message one every second for 8 seconds. So a total of 8 messages, one right after the other. And if it receives no responses, then it will actually place switch 1's port, where UDLD is configured, into a error disabled state, which is essentially down, blocking. And the reason for that is because remember, this link is about to come up to cause a problem. So to fix this, we're now placing it into essentially an administratively down state. A few notes here on UDLD. As I mentioned, you can enable this on any switch port. Most of the curriculum is going to talk to you about how it's only useful really on fiber optic media, and I tend to agree. Again, it's very rare that this would ever happen on any copper media, but you can actually enable this on a copper switch port. It will let you do that. The other thing I wanted to mention is in terms of configuring this, because obviously you have to configure one side at a time, you might be asking, well, if I wanted to configure UDLD aggressive mode, wouldn't it just place this first port into error disabled right away? Because obviously this other side doesn't have UDLD configured yet. I haven't gotten over to that switch yet, so it won't be able to respond. And the answer to that is no. UDLD won't do what we just described until it knows that it has seen a switch on the other side of the link before. So if you turn on UDLD on switch 1 and you haven't turned it on switch 2, switch 1 essentially is operating passively. It won't actively seek out those messages because it knows that it's never seen a UDLD message before from switch 2. But the moment you configure it here, UDLD is going to reach out to switch 1 and say, "Hey, are you configured for UDLD?" Switch 1's going to say, "Hey, yeah, I am totally. Let's sync up and we'll become essentially UDLD neighbors." At that point, we'll be bound to this. But before that, no, we can configure it as many. We can take as long as we want, and until it sees the switch on the other side, it won't impact anything. So I wanted to take a quick detour and mention a feature that I left out of the PowerPoint earlier, and that is loop guard. Now, loop guard has a lot to do with UDLD, and it can get very confusing between the two because they actually solve kind of the same problem, just in a different way. Now, LoopGuard is going to sit on, we're on switch 3, as we were before. And again, the BPDUs are being sent from switch 1 through switch 2 to switch 3. And that's why this link is getting blocked, because that's not the preferred path. The preferred path from switch 3's perspective is through port 2. So we have a blocked link here. And we are going to cause the same problem we did before, some sort of a fiber cut that makes this a unidirectional link. But we don't have we don't have UDLD configured. Instead, we're going to use LoopGuard. LoopGuard is going to see that on a blocked port, and this is only relevant to blocked ports, by the way. On a blocked port, it sees that the BPDUs have stopped being received. We're no longer receiving BPDUs on a blocked port that we were expecting. Now, LoopGuard is configured on a global, or I'm sorry, it's actually configured on a switch port basis. You can also configure it globally as the default, but it is a per port configuration. And we would configure that on ports that we would expect to stay blocked in a converged topology like this. Now, if the BPDUs stop coming and the max age timer times out, the default behavior for spanning tree is to bring this link up, because now it's good. However, as we noted before, that's a bad idea in a unidirectional link environment like this, because we still have a forwarding path in both directions. So LoopGuard is actually going to do much the same thing that UDLD aggressive mode does, and it's going to immediately place this switch port into a state called loop inconsistent, which is functionally the same as error disabled. The only key difference here is that by default, whenever LoopGuard disables a port in this activity, when it places it into a loop inconsistent state, and all of a sudden the BPDUs that it saw before start flowing back in again, maybe somebody fixes the link or whatever happens, it's gonna place that port back into the spanning tree listening learning kind of phases, which actually gives it the opportunity to become a root port or a designated port. But if that's the only change in the topology, it's going to again see that the cost is not as good as the other port, so it will go back into a blocked state. But it will force that port to go through the regular spanning tree phases. Now, you might be asking yourself, so what are the differences between LoopGuard and UDLD? Because it seems like they really accomplish the same purpose. And they do. They really actually do the same thing functionally. They're used for the same purpose, and that is, again, just to prevent the inadvertent forwarding of traffic that we did not want to forward. If we bring a link up that's supposed to be blocked, we're basically automatically introducing a bridging loop into our environment, which is bad. And both features do the same thing in preventing that. But now the reasons for using one or the other, and the I guess the underlying, really the physical actually attributes of the network, is really where you would want to choose one or the other. So first off, I would say UDLD is much better at catching wiring issues, layer 1 cabling, that kind of thing, because the messaging that it uses is really built for that. I'm going to transmit a message in the direction of switch 2, and if I don't receive a response back, then one of those pairs isn't working, and I'm just going to say, you know what, error disable the port and don't deal with it. Now, LoopGuard is different because LoopGuard works on just the receipt, or I guess the expected receipt of BPDUs. So in that sense, it's not as good at catching miswiring issues, but it can catch other things that might cause the basically stop some sort of situation other than cabling where a BPDU would no longer be received from switch 2. Also, it stands to note, LoopGuard works per VLAN, so if you stop receiving BPDUs on VLAN 9, but the BPDUs are still coming in on VLAN 10, it won't shut the port. UDLD shuts down the entire port physically, admin down. UDLD doesn't, or rather LoopGuard doesn't do that. LoopGuard will only place that port into a loop inconsistent state on that VLAN. So other VLANs traffics can come through. So if the issue is only on one VLAN, then you're really keeping the failure to a minimum. Also, it stands to note that the UDLD cannot automatically recover the way that LoopGuard can. When LoopGuard sees the BPDUs come back in that it was expecting, it puts the port into forwarding right away, or rather, I'm sorry, not forwarding. It places it into listening. It goes through the normal spanning tree phases, but it does so automatically. Whereas, in order to get that same functionality with UDLD, since UDLD places that port into error disable, you have to use the error disable recovery feature that's present in Cisco iOS that says, hey, after so and so seconds of being in error disabled mode, come back online. But that's not the default, so you do have to configure that if you're using UDLD. So that brings us to the end of this video. I'm going to try to keep it under an hour. I got some editing to do, but we'll see if we can get it done under there. So this being really my first video, I have 2 other videos out there on keeping it classless labs, but those are obviously less, the content is much more aligned with CCNA. I would like to ask for some constructive feedback on these videos. I'd like to do more of them because I feel like they help me study, frankly. Being a little selfish there, but I'd also like to share this information as I learn it. There's a certain format where this whiteboarding comes in handy, and it's hard to whiteboard and publish those images onto the blog and have it mean anything. I think that the whole concept of video-based learning when it comes to doing those whiteboarding sessions makes it really, really powerful. I mentioned Jeremy Char earlier. I think that's one of the ways that he teaches so well is because he demonstrates this stuff on a whiteboard in addition to actually getting into the command line, which I would also like to do more of in this video series. So long story short, just please let me know. Hit me up on my blog, keepingitclassless.net, or contact me via Twitter at Mearden, and let me know. I'm always open to new ideas. Hey, you should probably do this differently. You should probably not ramble on so much as I know I tend to do. Things like that, totally welcome. Just let me know, and I'll continue to push out content like this as I move forward through the CCIE Written and then hopefully into the lab. So thanks for watching, and I will see you on the next one.